Right. So as you get your means, so like I calculated mine and I put them up on the dot plot here. As you find your sample means, come up here and touch where your 4 dots should go. If you accidentally put a dot in the wrong spot, well, let me change that size there because that's way too small. Right, so if you accidentally put a dot in a wrong spot, like down here, the back arrow is right here, and that'll just erase it for you. All right. So as you find your means, come up and touch to put your dots up. It does have to be one finger at a time, because if we start getting double touches, then it's going to start to zoom in and zoom out. Oh, that's okay. Just hit the back button, and there, they came back. Right. Nice. Everybody that's not currently waiting, have you put yours up? Okay, I just want to make sure that I don't start talking before we get everybody's sample means up. It's kind of cool. I can watch it over here too. There we go. There we go. Everybody else has put up their sample means, correct? Awesome. It's fine. There you go. Fantastic. All right, so what does each dot on the poster represent? What do each one of these dots represent? A mean of 4 scores? How many scores did you write down? 5 scores, because we divided by 5. And so you had a random sample of 5 students and the mean score calculated for that sample. Each one of these individual dots is representing a random sample of 5 students and then the average of their test scores calculated for those 5 students. Get our dot plot back up here so we can look at it. So just looking at this sampling distribution that we have calculated, I'm going to go ahead and write that up here, sampling distribution. This is a, woo, that's way too big now. It's good for dots. It's not good for writing. This is our sampling. Sorry, simulated sampling distribution. Of X bar. What does X bar mean again? A sample mean. So each one of these, like this guy right here, that is a sample mean. This one right here, this is a sample mean. Every single one of these dots is a mean test score for 5 students in the class that I selected from. Looking at this here, ballpark for me where you think the true test average is. Between what? Between 80 and 85. Let's see if we can narrow it down a little bit more. I like that. Between 80 and 85, do you think it's closer to the 80 or closer to the 85? Probably closer to the 80. So tell me about where to draw this. Give me a number. I heard 82. You said what? 82. So right here, this is our guess for mu. All right. Mu, actually, for this test, because like I said, this was a test that I gave in another class, so I had the average there, was an 80.52. That was the true mean, 80.52. Did you guys guess reasonably close to that, considering how spread out our graph is, how spread out our dot plot is? So do you think this simulated sampling distribution, the mean of this, would be a reasonable, unbiased estimator for the true mean? Yeah. How do we decide that again? How do we decide if it's unbiased? It was in yesterday's notes. Yes. So this would be unbiased. Mean of the sampling distribution was approximately equal to mu. We say equal, but as long as we're getting close. Statistics, we want to get reasonably close with things because we're already talking about estimates here. I'm going to change that to an equal sign because that's what your notes has from yesterday. So we got very, very close with that. A sampling distribution shows the means calculated from all possible samples of size 5 from the population. Is this dot plot here a sampling distribution? Remember, a sampling distribution shows the means calculated from all of the possible samples of size 5. Is our dot plot a sampling distribution? No, why not? There's not every single one. I want you guys to calculate how many possible samples there are. Yesterday we did this by using combination. How many test scores did I tell you there were total up there? 44. There were 44 total test scores. And we're picking out samples of how much? 5. So you need to do 44 combination 5 to calculate how many total possible samples there were. On which kind of calculator? The Texas Instruments. You push the math button and then you arrow over to where it says PROB for probability. So you have to put in the 44 first and then math, and you arrow over to probability. And I think it's option 2 or 3 on there. Option number 3, thank you. What'd you get? Did we have 1 million dots up there? So what's that represent again? That 1 million something something? That's all the possible sample groups of 5 from this group of 44 students that we could have had. So there would be 1,086,008 possible samples of size n equals 5. So no, we did not take all the possible samples. We got a lot of them. We've got 20 people in here today plus me. Everybody did 4. So we had what, 44 dots up there? No, 4 times 2, 84 dots up there. That's not bad, but it's nowhere near 1 million. We took a random sample of 5 test scores at Rockford High School, and we got a mean of 68. Is this convincing evidence that the Rockford students did worse than students at our school? Or is it possible that Rockford has the same average? Let's go back and look at our dot plot. Where would a 68 be? Right, yeah, right where that purple dot is. So if I were to cordon this off right here, and I look at 68 or lower, how many dots are there total? 7 out of, we said there were how many dots total? 84. Calculate what that percentage is for me real quick. You said 8 point what? 8.33 repeating. Is that convincing? Where's our threshold for convincing evidence? 5%. Are we above or below that threshold? We're above. So is that convincing or no? Not convincing evidence. All right, so I would say no. Oh, hello, paper drawing on my screen. There is an 8.33% probability of observing a mean test score of 68% or less when the true mean is 80.52% purely by chance. (8.33%) while rare is not sufficiently rare or is not unlikely enough to suggest they did worse. So it was rare, it was not sufficiently rare. We're pushing like a 10% probability, so not likely to happen, but not rare enough to catch our attention and go, hey, wait a minute, I don't think that this sampling distribution would be the same to describe Rockford. Once you get that copy down, flip your page over. We're going to copy down our important ideas for the day. If you are not done copying down what's on the screen, go ahead and snap a quick picture. All right, big ideas for today. Evaluating a claim. When we go to evaluate a claim, we assume that the claim is true. And then we're going to create a simulated sampling distribution. Once we have our simulated sampling distribution, we're going to find the percent chance of getting the observed result. So the claim that was made was that, like on that very last question, claim that was made was that Rockford performed about as well as our students on that same test. We created a sampling distribution. We actually did that part first. And then we found the percent chance of getting that observed result, 68% or lower, in a sample of 5 students. If we find that it's less than a 5% chance, that is convincing evidence against the claim. So again, the claim was that Rockford did the same. We got more than 5%, so we did not have convincing evidence against that claim. And once you are done copying that down, I want you guys to try the check your understanding that's down below. It looks like most people are finished copying down the majority of that. Let's see what we can do in about 5-6 minutes working on the bottom. So for number 1, I want you to identify the population. So what is the whole group that's being looked at? What is the parameter that they have defined? What is the sample that is being described in the situation? And what is the statistic that was calculated? Does any evidence exist? What are the possible explanations for any evidence you might find? And then down at the bottom, you're going to evaluate that claim. Wait, let's see what we got. What's the population here? What is the population that's being described? All the pennies. All the pennies specifically in this container. That's the population that Jenna is looking at. What's the sample? The 50 pennies, right? She's going to take out 50 pennies and figure out how many of them are pre-1982 copper pennies. What was the statistic that Jenna found? We said how much? That's going to be our parameter. That's our population. So that one goes right here, 13.2% or 0.132. That's our parameter. What did Jenna actually find? Because that would be the statistic. 11 out of 50 or 0.22. Does she have some evidence that more than 13.2% of her pennies are pre-1982 copper pennies? What was the parameter again? 13.2. What was the statistic? 0.22. Does she have some evidence that she has more pre-1982 pennies than are apparently in circulation total? She has some evidence. What are two possible explanations for that? Is it possible that in the entire container, it is the same as what the full population parameter is? That it's 13.2 in her entire container? Is that a possibility? And that she just got really lucky when she picked out her sample. That is possible. What's the other possibility? So we have one possibility that the true population mean in her container of pennies is that it really is 13.2%. She just got lucky with her scoop of 50 pennies. What's the other possible explanation for the difference that we see between the parameter and the statistic? What's the other possible explanation for why this could be different? Yeah, that in her container, she actually does have more than 13.2% copper pennies. So population, all the pennies in the container. Parameter, remember we use P for parameter, or when we're talking about a proportion, our parameter is P. The statistic, 11 out of 50, that's P hat. Because we're not talking about the whole population here. We're not talking about the whole population proportion. We didn't dump out every penny in that jar. Anytime we calculate a statistic, we have a different notation for that. Does Jenna have some evidence? Yes, she does. 22% is bigger than 13.2%. We don't know yet whether it's convincing evidence. We just know that there appears to be some evidence, so we're going to keep moving forward. So there's a dot plot that was made using technology to simulate 100 simple random samples of 50 pennies from a population of pennies in which it really is true that 13.2% are pre-1982 copper pennies. So the dot plot shows P hat, the sample proportion of copper pennies for each of the 100 samples. So in this case, each little dot is not X bar, each little dot is P hat. We're not calculating the average, we're calculating the proportion. How many out of 50? You guys okay if I go to the next screen so we can actually see that dot plot? Snap a quick picture if you need to. So here's the dot plot that was made, assuming that it really is a 13.2% pre-1982 pennies. They did 100 simple random samples of 50 pennies, and each of these dots represent the proportion. There is one dot over here at 22%. That's this guy right here. How many times did they pull random samples where the actual population parameter was 13.2%, where we got 22% or more? How many dots meet that criteria, 22% or more? 4. Out of how many simple random samples? They did 100 random samples. There were 50 pennies in each sample. But this is 100 dots up here. So 4 out of 100, what is that as a percent? 4%. Is that convincing evidence that she has more pre-1982 pennies than the US, I don't even know what department that is, says are in circulation? What's our benchmark again? 5%. If we're more than 5%, we say that's not convincing evidence against the claim that this is just happening by chance. We're under 5%. So do we or do we not have convincing evidence? We have convincing evidence that this claim that it's really the same as what the US government says is in circulation, we just got lucky with this scoop. Assuming that the container has 13.2% copper pennies in it, it's unlikely, only 4%, that we got a sample of 50 with 22% or greater copper pennies purely by chance. This is highly unlikely. Where did I put my iPad? Again, each one of those dots represents the proportion from one sample of 50 pennies, which had 22% copper pennies. Remember, if it's more than 5%, we do not have convincing evidence against our claim. And the claim is always assuming that this is just chance. There's nothing really going on here. We just got lucky. We always make the claim. We always take the skeptical side of the claim. Now, this was just luck. If there's less than a 5% chance of it happening just by luck, then we say that we have convincing evidence against that argument. All right. Tomorrow, you guys have a work day on the 7.1 homework. It is due by the end of the day tomorrow. And I will also pass out your final exam review packet to you tomorrow. Have a great rest of your day, guys. I'll see you tomorrow.